grade 12 mindsetters, welcome to today's Physical Sciences show. Today we have a special revision lesson on acids and bases. We have selected highlights from lessons shown earlier in the term to help you revise. Please post your comments and questions on our Facebook page on facebook.com/learnextra or on Twitter @learnextra so we can help you with your revision. You can also download the notes for today's show from learn.mindset.co.za or click on the link on our Facebook page. Now it's time to get on with today's lesson.
Now the first thing we're going to look at is our basic properties of acids and bases. So starting with acids, okay. Now the thing here, oh look, pen has decided it doesn't like me. So acids have the following properties, okay. They are sour, they taste acidic. Hopefully not too many of you done this, but what kids do is they like to eat things around them, and so some of you have possibly eaten ants, and ants are sour. When you're little, did you? Never mind, it's not something I would do.
Okay.
Okay, and flying ants are a delicacy. I know in upper middle Africa somewhere they actually fry them. I had a friend who liked them. Anyway, she got very excited when flying ant season came about, but that's besides the point. Anyway, they conduct electricity in a solution because they create ions, okay? They can neutralize a base, okay? We're going to talk about neutralization and titrations very specifically next week. For now, it reacts with a base, and it produces a metal salt. Now remember, grade 12s, a salt is just a classification of a compound. Doesn't mean it's making table salt. That doesn't mean it's making sodium chloride. It simply means it's making a compound that is ionic, okay? Which means that salt is a metal plus a metal and a non-metal bonded together, okay? So be careful there. And water, and there's an increase in the concentration of the H plus ions. Those H plus ions we often are actually H3O plus ions, the hydronium ion, okay? Because when the acid ionizes, we get the H3O plus ion at the end, but that becomes difficult to say all the time, so we just keep it as H plus, but it's the same thing, okay? The H3O plus ions. Then, a base, in terms of its very basic properties, bases have a bitter taste, and this is another thing some of you would have done as children. It's one of those things, it's how we learn, it's how we explore, it's how we learn about the world around us. We try and eat soap. Did you ever do that, Looney?
Yes.
Yes, of course. Okay. And now it gets hard because now we have liquid soap, so we've got to be really careful.
I tried liquid soap and like soap.
Oh,
both.
wow.
Yeah, I was one of those children.
Moving on. So, but it's got that horrible, bitter, soapy, you can taste, it's horrible. All bases would taste like that if you could taste them. Remember, you don't taste things in the lab. They feel soapy, like soap, okay? Even things like your really, really strong bases like sodium hydroxide, NaOH, feel soapy to touch, okay? That slippery, slimy feel. They also conduct electricity in solution because they create ions when they dissociate. They neutralize an acid, so it's the opposite to an acid, okay? Creates a metal salt, same metal salt as we had before. It's an ionic substance, non-metal and metal bonded together in water. Alkalis, now here's a new term here, guys. A base generally is a solid, okay? Though, yeah, generally is a solid. If the base or a basic substance can dissolve in water, it is an alkaline, okay? It turns, we use the term alkali, okay? It's just a fancy term to say it's a base dissolved in water. Alkalis increase the concentration, now watch here, of the OH minus ions. H plus for acids, OH minus for bases, okay? And it is the OH minus ions concentration, or, and sometimes this is the way to look at it, it decreases the H plus ion concentration. Same thing, okay? So, that brings us to our definitions, and we have two. Grade 12s, you must know both, okay? And I am going to pronounce the first one and his name wrong. I'm sorry. It's just one of those things. There's lots of words I don't like to say in science, and this is one of them. One of the first definitions of an acid and base was done by Arenus, okay? And what he said was, for an acid is a substance that releases H plus ions in an aqueous solution. So, for example, when I have HCl, which now dissolves in water, okay, so we react it with water, what happens is we end up, we get the Cl minus ions, but we also end up with H3O plus, which we just write as H plus most of the time, okay? So every single acid has hydrogen in it. It has to have hydrogen in it, okay? Otherwise it can't be an acid. So this definition for an acid is great because it fits for every single acid. There is no exception to this. Then we come to his definition of a base. And he said a base is a substance that releases OH minus ions in a solution. That's okay when you are looking at sodium hydroxide. Okay, it's got OH in it. Okay, and when we say it dissolves, it ends up Na plus and OH minus. But what happens when you have something like sodium oxide? Sodium oxide is a base. Okay, it's an alkaline, it dissolves in water, reacts with an acid, neutralizes it. Okay, but when it does that, it doesn't actually create OH minus ions. So there's a problem with this definition in that it doesn't encompass enough of the bases, okay? It's very specific to bases with OHs in them. And this is where the error came in, and this often happens in scientific processes. People give definitions, they have models, and then they do more investigation. Someone else comes along and goes, oh, hang on, wait, but it doesn't include this, or this needs to change. So what happens is now we have to have a definition that takes everything we know and makes it broader, okay, so we can encompass everything. So that brought us to Bronsted-Lowry, okay? Guys, please, that O is written with an O and a little line through it because it's not English, and I can't remember which nationality they are, okay? It's a combination of scientists who were given credit for this, and what they said is, and these are nice ones, these are the definitions, is they said an acid is a proton donor. By a proton, they mean an H plus ion. And now you say, oh, hang on, wait, Tracy, H plus ion, how's that a proton? Remember, hydrogen only has one electron and one little proton, and during a chemical reaction, along the way, it loses its electron, okay? So it says, bye-bye, electron, and that becomes what we call a naked proton, okay? I call, in my classroom, hydrogen is the flasher, okay? Because he's a naked proton. What can I say? It's very rude. But he's just, literally, the H plus ion is a proton. That's what it is, okay? So when I talk about a proton donor, I mean an H plus ion, okay? A base is a proton acceptor. Two halves of the same coin, basically. An acid gives its proton away, doesn't like to be on its own, so that proton gets taken by a base. You've done a little bit of redox in grade 11. Remember, redox reactions was the transfer of electrons, okay? This is the transfer of protons. And because of that, we actually call this a protolytic reaction. Okay? Proton. Okay? It's not an electrolytic reaction. We don't have electrons. It's protolytic. So Bronsted-Lowry give us a much better definition of what an acid and a base is. Acid is a proton donor. Base is a proton acceptor. That's something you really must keep in the back of your mind when we get to the section on conjugate acids and bases. Because you've got to look at your formulas and go, can I give away a hydrogen? Can I take a hydrogen? Okay, and how does it change? Nitrogen dioxide, okay, and sulfur dioxide can be prepared according to the following equations, respectively. So here's the first one, copper plus, please remember that those two together give me HNO3, okay? HNO3, don't worry about the balancing. That gives me copper, essentially gives me copper nitrate, NO2 and water. Then we have here, this is sodium sulfate, Na plus, okay? It should be Na2SO3, sulfite, sorry, and hydrochloric acid, and that gives me hydrogen sulfite and sodium chloride, or salt, okay? And water. Now they ask you, what is an acid-base reaction? Definition, straight definition. An acid-base reaction is a reaction in which there's a transfer of H plus ions, or it's a reaction in which there's a transfer of protons from the acid to the base. That's what an acid-base reaction is, okay? Transfer of protons, okay? Now, I chose this very specifically because I needed you to see some things, okay? In terms of what's happening with a whole bunch of stuff. Now, they ask you, which of these two reactions is an acid-base reaction? And now some of you are going, okay, Tracy, we don't even know where to start. So let's take some of my scribbling out and let me help you. Okay, let's consider equation 1. Okay, now equation 1, I have a metal and an acid, okay, and I said to you that the general reaction with the metal and acid is that we should get a salt and we should get hydrogen gas. Okay, so now we look at this and we go, well, Cu2 plus and 2NO3 minus together give me copper nitrate. That's a salt, but what's the problem? I've got NO2 and H2O. So I'm really starting to think, not so much. Another thing we need to look at, okay, the copper over here, this little bit of remembering stuff from grade 11, has no charge. The copper over here is now 2 plus. The copper lost 2 electrons, okay? The copper loses 2 electrons. And the copper, the hydrogen over here, the H plus, doesn't actually do anything. So first of all, I've got a loss of electrons here. There's a change in oxidation number. That immediately tells me it can't be acid and base. Okay? So it can't be number 1. Let's check for number 2. Sodium sulfite, that's the salt, okay? And hydrochloric acid, we don't know the general one for this, but let's see what happens. Okay? Now, watch what you see here. This is H plus, okay, and Cl minus. Watch what happens. The Na plus stays Na plus. That's not a problem. The sulfite actually takes this hydrogen from the chlorine in order to create the hydrogen sulfurous acid. Transfer of protons, transfer of H plus. The chlorine loses its poor little electron, becomes Cl minus. Poor little chlorine, okay? So, answer to the question, number 2. Okay, now, they say to you, write down the acid-base conjugate pairs. Obviously, you need to have identified the correct equation, okay? Now, when they ask you this, and I so didn't leave myself enough space, so I'm going to do it over here. Please be careful how you write this. You want to make it very, very clear as to which is which. So rewrite the equation, and I've just got it here again so that I get it right. So we've got 2Na plus, okay, I'm not going to worry about the phases for now, SO3 2 minus, plus 2HCl, and then we've got H2 SO3, 2Na plus, and we have the 2Cl minus. Now, first and foremost, did anything happen with the sodium? No, sodium plus. She's just there. Okay. So, we realized that the hydrogen was given its, the hydrochloric acid was given its hydrogen to the SO3 2 minus. Okay, which means the HCl is an acid. Okay, that's my acid. And the SO4 3 minus is my base. The Na plus is a spectator. It's there because I needed something to keep the SO3 2 minus company, but it's not actually changing. The HCl gives its hydrogen to the SO3 2 minus, That makes this here become an acid. So this is a conjugate acid, okay? I'm not quite finished yet. And the Cl minus, which I've squeezed right in at the end, has become, I'm just going to put Cb conjugate base. I'm still not done, because they wanted us to identify the pairs. The HCl goes with the Cl minus, and this is my conjugate acid base. Ooh, just pretend that's a T. But wow, should not have broken the pen. Okay, conjugate. But I write faster. Acid base pair. Okay, and then your other one is the SO3 and the H2SO3, and that's also a conjugate acid base pair. Guys, you want to make sure that your examiner knows exactly what goes with what. Write it out. Okay? They just said identify the pairs. That's what we've done. Okay? Here, the better you do, the more accurate you are with identifying this, the better it'll be. Okay? So be careful when you work through this. Now, along the way, we've actually answered the last question, because the last question said to us, identify a spectator ion in this reaction. It's the Na+. Okay? Just like in redox reactions, which you've done a little bit about, we can have spectator ions. Proteolytic reactions can have spectator ions. Okay, ones that are there, but they don't actually take part, so they don't change anything. They don't gain or lose hydrogens. Nothing happens to them. They're the same on both sides. Okay.
Okay, guys, I hope you're enjoying this revision session. If you need help, remember to post on the page or send an email to helpdesk@learnextra.co.za. Now it's time to take a quick break, but don't go away. We'll be right back. Welcome back, guys. We have some great news to pass on to you. We will be bringing you winter school from the 30th of June till the 20th of July, starting at 10 a.m. every weekday. To get the full schedule, visit our website, learn.mindset.co.za, and look for the winter school link. Join us. It's going to be a lot of fun. But now it's time to get back to the lesson.
When HCl is bubbled through distilled water, it ionizes. Oh, look, that's the eraser. It ionizes as a result of proton transfer. Okay? The equation for this ionization process is given, and this is actually a really important equation. You're going to see it lights. So what happens here is the HCl comes along and it actually gives its hydrogen to the water. Now, we say this is ionization because HCl, hydrochloric acid, is a covalently bonded compound, which means as a covalently bonded compound, it isn't made up of ions. So when I force it to become ions, when I dissolve it, it's ionization. Okay? We're not dissociating ions from each other. We're ionizing it. We're forcing it to become ions. And what happens is we get H3O plus and Cl minus. Now, first thing they say to you is provide a suitable name for the H3O plus ion. Okay? That doesn't mean John or Mary or Sue or whatever. Okay, that's not what they're asking for. They're asking for its scientific name, and hopefully you guys know this. It's hydronium. Okay, H3O plus is known as the hydronium ion. Okay, it's a hydronium ion. Now they say to you, what causes the solution to have acidic properties? So when we look at this, we go, okay, what is it about this part of the product side of my solution that says, why does it behave like an acid? What is it that makes it acidic? It's this. It's the presence of the H3O plus ions. Okay, those H3O plus ions, it's that ion that makes acids corrosive, that makes it so dangerous, okay? And the more of those there are, the more dangerous it becomes, okay? So it's an acidic property because it has the H3O plus ion, and we've had hydrochloric acid, HCl, okay, well, it's hydrogen chloride, it's in gas form, donate its hydrogen to the water, okay? Then, would the resulting solution be strongly acidic or weakly acidic? Now, it's not the wording's a bit unusual, but what they're asking you is is what we get a strong acid or a weak acid? Now here, this is where it's actually really important for you to, and I'm pretty sure your textbooks have lists of the most common strong and weak acids and bases. Please, you must know them. Hydrochloric acid, HCl, is one of our strongest acids that we use, okay, besides phosphoric, okay, and sulfuric. So it's a strong, phosphoric, not, anyway, moving on. It's a strong acid. The point here is because it's a strong acid, when the HCl ionizes in water, it produces a lot of H3O plus ions, okay? This is strongly acidic. There is a very high concentration of H3O plus ions in the solution because the HCl ionizes almost completely, okay? So what we'd want in there is, first of all, your answer is that it's strongly acidic. Why? Because there's a high concentration of your H3O plus ions, okay? Because HCl ionizes almost completely. Sure, my handwriting just gets better and better. Almost completely. See, I can't spell too. Good. Okay, now, what do we call a reaction in which proton transfer occurs? Well, I said to you earlier, this is a protolytic reaction. Okay, it's a protolytic reaction.
We're starting off with this idea of the equilibrium constant for water, Kw. Now, you'll remember that when acids and bases, in chemical equilibrium, we defined the Kc. Now, Kc is the same as Kw, just for this particular reaction. So what happens in water? In any glass of water, here I've got a glass of water, okay? At the moment, it's quite nice to drink it, but inside here, what's happening, apart from a few floaties that I can see floating around, there's an amazing chemical reaction that's taking place. Let me just have a sip. Oh, that's good. Now, even though I've had some water, there's a chemical reaction happening in every droplet of water. Molecule of water, which we write down as liquid H2O, collides with another molecule of water, liquid H2O, and they form this ion, which is called the hydronium ion. Hydronium ion. Okay? What is it really? What is the hydronium ion? Guys, it's a hydrogen ion that's surrounded by water. It's just added on. So let's just break this down so that you can see it a little bit easier. So I'm going to draw some stick figures. And we're going to say that's one molecule of water. And this is another molecule of water. And I'm going to draw it over here like this. And we're just going to say, let's pretend for a minute that this molecule on the left-hand side, that one, bounces into that hydrogen over there. Maybe we need to turn it. So let's just turn it so that it doesn't get close like that. And if it's in that position, guys, here's the interesting bit. What can happen is that there is a form of attraction between the hydrogen and the oxygen, because there's a lone pair of electrons there. In fact, two lone pairs of electrons. And there's the hydrogen ion. Now, you should know that this is an intermolecular force called the hydrogen bond. And it happens in water all the time, hydrogen bond. It's not a true bond. It's not sharing electrons at this point. It's just an attraction. But if it gets really close, what will happen, and I just want to undo something here so that we can see what's going on. So that was the hydrogen bond. Now, if it gets really close and it carries on and it's got enough energy, then those two electrons from the lone pair of the oxygen are able to attract and catch this hydrogen, that little hydrogen over there that's on its own. this one here, I'm going to circle it again. And instead of it staying attached to this molecule, what happens? It breaks its attraction over there and it stays fixed, now sharing those 2 electrons. Whereas this one now has a negative charge on it. So this one has more protons because that hydrogen has a proton, the one I've circled in blue. And this is a plus. That's your hydronium ion. And this second thing over here, that's called your hydroxide. Okay, very important for you to understand that this is happening all the time inside any glass of water. Okay? And as 2 water molecules fall into each other and they bump into each other, they make hydronium and hydroxide. The hydronium and hydroxide, being positive and negative, can collide with each other and make 2 water molecules. So what have we got? We've got a forward reaction and we've got a reverse reaction, and the rates of those reactions will be equal at a certain temperature. So we've taken a standard temperature. We've said let that temperature be 25 degrees, room temperature. It's average room temperature for most experiments. And we've said then we can have chemical equilibrium. The forward reaction equal to the reverse reaction, the rate of the forward equal to the rate of the reverse. That doesn't mean that the number of ions is equal to the number of molecules. Please no. The concentration of the ions, though, is a very important topic. So what we know at 25 degrees Celsius, we can write a Kw, which is equilibrium constant for water. And it's the ionization of water, or the auto-ionization of water. Auto just meaning that it's self-ionizing, water bumping into water, but it's the ionization of water when there's just water around. Okay? So remind me now that when we do this, the formula that we're going to use, we're going to take the product, the concentration of the product, and divide it by the concentration of the reactants. That's for any Kc. But we need to remember we can only do it for things that are aqueous or gases. What happens when we've got liquids? Well, when we've got liquids, they don't form part of the Kc expression. So the Kw here is just simply written as the concentration of the hydronium ion times the concentration of the hydroxide ion. And what we need to understand is that at 25 degrees, we find experimentally that this is 1 times 10 to the minus 14. Okay, that's the value at 25 degrees. So what's this telling us? Guys, think about it now. 1 times 10 to the minus 14. Is that a big number or is it a small number? Well, it's 0 and then comma and 13 decimal zeros, 13 places, and then a 1. That's an incredibly small number. Okay? Now, what we need to recognize is that if we look at the formula or at the chemical equation, for every 1 mole of that, there's 1 mole of that. So in the sample of pure water, what we can say that the concentration of the hydronium is equal to the concentration of the hydroxide. They're equal. And that shouldn't be surprising. For every 2 water molecules, we'll get 1 hydroxide, 1 hydronium in this pure water situation. So that tells me that if I want to get the concentration of these two, both of them, then it must be the square root of 1 times 10 to the minus 14. So let me put that into the calculator, and I'm going to say 1 exponent 14. I want to get the square root. So let's just take the square root of 1 exponent negative 14, and let's see what we get. And that you can see is a very small fraction, and it's equal to 1 times 10 to the minus 7. So That's equal to 1 times 10 to the minus 7. Guys, I'm tired of working with these very small numbers. The hydrogen ion concentration, or hydronium ion concentration, hydroxide ion concentration, 1 times 10 to the minus 7. So chemists thought, well, yeah, this is awkward. In any solution of water, I've got 1 times 10 to the minus 7. I'm going to get tired of saying 1 times 10 to the minus 7. Let's rather use a special scale that doesn't worry about the 1 times 10. Let's just focus not even on the negative. Let's just take that number, 7. Now, I know that this is not a maths lit lesson, but 7 seemed to be a good number. And what they then said is, well, how can we track that number, that power? Well, they then decided, well, we'll go and speak to the mathematicians. And the mathematicians said, well, there's a special function that we can tell you about. And it's called a log function. Some of you will have dealt with it at school. And we talk about log to the base 10. And we're going to say, well, what happens if we take the log to the base 10 of the hydrogen ion concentration, or the hydronium ion concentration? Well, it's going to give us that whole thing, the negative 7. So I'm going to make it negative log of the, and that will give me an answer of 7. Hey, that's really cool. So what would the negative log of the hydroxide ion concentration? 7 as well. And so they started to suggest that there was a scale that went from 0 all the way through to 14, but in the middle point, that's where they were equal. That was 7. This scale was called the percentage hydrogen, or the parts of hydrogen, or just pH.
I think it's time for a break now. Don't go away. We'll be right back. Welcome back from the break. Let's not waste any time and get straight back to today's revision lesson. Over to you.
In an acid-base reaction, 500 centimeters cubed of a solution of sodium hydroxide is completely neutralized by 680 centimeters cubed of a solution of sulfuric acid. The equation for the reaction is given as H2SO4 plus 2 NaOH gives you Na2SO4 in aqueous solution plus 2 H2O. The pH of the base solution before any acid is added is 3,80 at 25 degrees Celsius. The question part 1 says, show by calculation that the concentration of the sodium hydroxide solution will be 0,631 mole per decimeter cube. Wow, guys, that's quite an involved calculation, but it's not too difficult as long as you remember the information that you've been given. Now, we had just defined what pH is, and we're going to need to use it here. Remember what it says? The pH is 13, which I'm going to write as negative log to the base 10 of the hydrogen ion concentration. Hydrogen ion, I can write as H+, that's fine, is equal to 13,80. Now, how am I going to find out what the hydrogen ion concentration is? Because remember, I don't just want the hydrogen ion concentration. I must find the hydroxide ion concentration. Yay! Be careful here. We need to be very careful and make sure that we understand exactly what's going on. And we'll take it one step at a time. So first of all, let's uncover what the hydrogen ion concentration is. So we're going to need our calculators, and we're going to need to undo this whole process. And I'm going to undo it in my head first of all. And first thing that I'm going to do is I'm going to say, I know, therefore, the log to the base 10 of the hydrogen ion concentration is equal to negative 13,80. Okay? The next thing I'm going to do is I'm going to undo this logarithmic process. And I'm going to say How do I undo the log? Definition of log, if I want to get H plus on its own, then I'm going to need to take 10 to the power. I'm going to take that base and I'm going to arrange it as the power of 10, and I'm going to say that must be 13,83. 13,80. Let's put that into the calculator and see exactly what that comes out as. So, in other words, what I want to do is I want to undo the log form, and I'm going to say, what is 10 to the power? Now, here I'm going to use the XY, and if I can find it for a minute, I've just lost it. Let me find it. There it is. I want second function, and I've put the two things in place. Let me just undo that. I'll delete it. So delete that, and I'm going to go second function, 10 to the power, and I want negative 13,8. Hope you've got that. Not difficult. It's with the log. I hope you could see that. And we get an answer of 1,58489 times 10 to the minus 14. Now, let's write that down. 1,48 times 10 to the minus 14. 1,58 times 10 to the minus 14. So that's the hydrogen ion concentration. But that wasn't what the question was asking. The question was asking, what's the concentration of the sodium hydroxide? Now, here's the very important thing that you've always got to come back to. Remember, we dealt with, in our summary section, that whole ionization of water. That's the key to all these acid and base questions. I'm going to need to keep this number, and I've run out of space, so I hope you've got how to get from pH to a concentration of a hydrogen ion. I'm going to keep that number. I'm just going to move this, and remember that that's the pH, and the rest of the stuff I'm going to erase because I need to just get myself some space, and let's hope that we've got that. Give ourselves some more space over there. I'm going to write down pH. So I now know that the pH of the solution is not pH, hydrogen ion concentration. Whoa, what am I doing? That's very naughty of me. Hydrogen ion concentration is equal to 1,58 times 10 mole per decimeter cubed. Okay. Now, have a look at what's happening inside this solution. The solution is sodium hydroxide, which was a solid, and it's been dissolved in water. What's it done? I've increased the hydroxide ion concentration. Therefore, I reduced the hydrogen ion concentration. Let me explain that to you again. So if we look at the Kw, at the expression for water, H2O plus H2O goes to form H3O plus OH minus. And so what I'm saying to you is we've added to this sodium hydroxide. And we've added some sodium hydroxide, which was a solid sodium hydroxide. It dissolves. And so what have I done to this equilibrium? I've increased the concentration of the hydroxide. Hope you can see that. If I increase the concentration, it must favor the reverse reaction. If it favors the reverse reaction, it's going to reduce the hydroxide ion concentration, and at the same time, it's going to reduce the hydrogen ion concentration. It's going to go to that direction because we've added to the side. Le Chatelier tells us it's going to move, favor that side to reduce the added hydroxide to the concentration. Okay? It gets to equilibrium. We're told what the pH is. We now know that this concentration has been worked out. We also know, in terms of this water, that the Kw hasn't changed because we didn't change the temperature. Remember, only temperature change Kc or Kw. This is still at 25 degrees Celsius. So in Kw, what do we know? We know it's the hydrogen ion concentration times the hydroxide ion concentration, which is equal to 1 times 10 to the 14, negative 14. Okay? That doesn't change. What we do know, though, is that we've got the concentration of the hydrogen ion. We've got that concentration. We want to find the concentration of the hydroxide. So how are we going to do it? Not that difficult, I don't think. All we have to do is we take the hydrogen ion concentration and divide that into the Kw. So what we're going to say, the OH concentration, OH minus concentration, is equal to Kw divided by the hydrogen ion concentration. And what do we get? We get the following thing. We get 1 times 10 to the minus 14 divided by our number up there, 1 times 10 to, 1 comma 58. 58 times 10 to the minus 14. Let's put that on the calculator. Wow, there it is. It's on the calculator and it's a denominator. Now I'm going to do a little trick. I'm going to put it onto to the denominator. I'm going to push that button and I'm going to multiply by my numerator. 1 times 10 to the minus 14. 1 times 10 to the minus 14. And hopefully we get the right answer. The answer is 0.63. 0.63 moles per decimeter cubed. Guys, that's the concentration of the hydroxide ion. We were asked to find out the concentration of the sodium hydroxide. Yes, the concentration of the sodium hydroxide is the same as the concentration of the hydroxide. How do we know that? Well, in this case, look, for every 1 hydroxide, there has to be 1 sodium. So the concentration of the sodium hydroxide is the same as the concentration of the hydroxide ion. In some cases, if we had to take a look at something like the stuff that we were working with, like the strong acid, sulfuric acid, it's not only a strong acid, it's diprotic. It means if we know the hydrogen ion concentration, we don't know the concentration of the sulfuric acid, it's not the same. We have to take the hydrogen ion concentration and divide by 2 because there are 2 hydrogen ions for every one of those. I hope you can see that with sodium hydroxide, though, it's a 1-to-1 ratio. Okay, so we've answered the first question, and I love this question because they give you the idea to get it right. We know that we got that answer. Let's just check our decimal places on the calculator, and you can see if we rounded it off to 3 decimal places, which I was naughty in not doing, let me just add in the 1 there, because then it would be all correct. So let's go to the second question now. It says, what is the difference between a strong base and a concentrated base? Guys, this is an important theory question, and it comes up all the time. A strong base dissociates completely when placed in water. That means something like sodium hydroxide will produce sodium ions plus hydroxide ions. For every 1 mole of that stuff, you'll produce 1 mole of this, you'll produce 1 mole of that. The ratio is 1 to 1 to 1. There's nothing left over. It ionizes or dissociates completely. We think that there are ions in the sodium hydroxide. It's an ionic solid. And all that happens is it separates. So that's what strong means. Strong acid, same thing. It ionizes. It forms ions for the first time completely. So there will be no molecules. This is competition. Should I be a molecule or should I be an ion? When they are strong things, they are ions. If they are weak acids, then some of them go to be ions and some of them stay as molecules. And we'll come to that shortly. Now, what's the difference between that and a concentrated acid? concentrated acid simply means that the concentration is the number of moles per volume. If something is concentrated, it tells you that there's a high number of moles in a small volume. But we could have a strong acid and it could be dilute. The opposite to concentrated is the word dilute, which would mean there are a few moles in a large volume of water. Now, understand this. From grade 11, you need to remember that things that are strong stay strong. Sodium hydroxide will always be strong. Sulfuric acid, hydrochloric acid, nitric acid, always be strong. But something like acetic acid or oxalic acid, they'll be weak. They're always weak, they're not strong. Okay, let's move on. Calculate the mass of salt. Now, we're going back to our previous question. The mass of salt used to prepare the base solution. So, now, how do we do this? We've got to get the mass of salt used to prepare the solution. So, if we go to sodium hydroxide, and it's going to form a solution, we're going to say, in terms of this, let's take that as the solid, and we're going to say that it goes to form sodium ions plus hydroxide ions. We're not looking for anything fancy. This is aqueous. This is aqueous. And remember what I said, that ratio is 1 to 1 to 1. So if I know the concentration of hydroxide ions, which I was actually given, so even if I couldn't work it out, I've been given it over there, 0.63 mole per decimeter cubed. So we know that concentration, 0.631 mole per decimeter cubed. And another way of writing that mole per decimeter cubed is to say 0.631 with a capital M, molar. Now, that's the concentration. It doesn't tell us the number of moles. Let's see what the volume was. We're told solution 500 centimeters cubed. So we want to get the number of moles. That's what I'm interested in, is the number of moles. Number of moles is equal to concentration times volume. Concentration is equal to number of moles divided by volume, but you can multiply these out like this. So I've got my concentration. My volume was 500 centimeters cubed. I need to change that to decimeters cubed. I'm going to write 0.631, not 500 now, but 0.5. And this will give me my number of moles. So let me do that. 0.631, I'm not going to use that because it's got too many decimal places. 0.631, I'll use the 3 decimal places because I was given it, times 0.5 for the decimeter cubed container, and I'm told that I've got 0.315, and I'm going to work to 3 decimal places, and I'm going to say 0.316, 0.316 moles. That's the number of moles I've got. Now guys, what you've got to recognize, 1 mole of this came from 1 mole of that. So what am I going to do to get the mass? The mass, remember, this is stoichiometry, revision from grade 11. The mass, and I'll just have to work over here, mass is equal to the number of moles times the molar mass. The molar mass of sodium hydroxide, it's one that I've learnt, molar mass is 23 plus 16 plus 1, which is 40. You might want to take a note of that. Grams per mole. Comes up so often, you might as well learn it. So we're going to take the number of moles times 0.316 times 40. This will give us the mass of sodium hydroxide. Okay, 0.316 times 40, and we get an answer of 12.62. 12.62 grams. And there we go. So we'll need 12.62 grams of sodium hydroxide, the solid, and we're going to dilute it to make sodium hydroxide solution. Last question for this is calculate the number of moles of the hydronium ion effectively used in the neutralization process. Wow, guys, this is a really important question. So, we need to understand that we started off with, let's go back to our figures, and we're going to work with the equation. We're going to work with this equation. We're going to work with H2SO4 plus 2NaOH, giving us sodium sulfate plus water. So I'm going to write that equation down, and let's see if we can work with it. We're going to start with H2SO4 plus 2NaOH gives us Na2SO4 plus 2H2O. Now, what do you notice here? I hope you can see 1 mole of that reacts with 2 moles of that to produce 1 mole of that to produce 2 moles of that. What we're really interested in is this ratio, because we've just worked out that the hydrogen ion concentration, or the hydroxide ion concentration back here was 0.631. 0.631. This is 0.631 mole per decimeter cubed. Got it? So that means that what we've got is the number of moles. That was concentration. Rather, let's work with number of moles. We've got the number of moles as 0.316. Rather work with that, because we'd prefer to work with number of moles. We will ask and calculate number of moles, so that's better. So let's work with that number, 0.316. 0.316. 0.316. Now, how do we get to that number of moles? We're going to go from here to here. We need to use the ratio 2:1. So how are we going to do it? Well, it's easy. If I went from there to there, I would divide. If I used the pink arrow to go from 2 to 1, either multiplying or divide, I divide. What do I divide by? Divide by 2. So if I'm going to start at this point, what am I going to do? I'm going to divide by 2 to get me my answer. So let me pick that up. And I'm going to say 0.316 divided by 2 gives me the number of moles of the sulfuric acid that I need. 0.158. But now, notice something. That wasn't what I was asked. I was asked the number of moles of H+, H3O+. And what you should be able to see, I've calculated the moles of sulfuric acid. But for every sulfuric acid, look here, what do we notice? There are 2 hydrogen ions. So what do I get to get the hydrogen ions? I have to multiply by 2. And all that is saying is that if I multiply that by 2, I'm going to get 0.316, which is moles of hydrogen ions. Okay.
We've come to the end of today's show. Thanks for joining me and for chatting to me during the show. Remember to visit our website, learn.mindset.co.za, to get the notes and to watch the videos from the term. Goodbye.